Okay, and welcome to our next day. And today, of course, as always, we start with putting our cell phones in the caddy and then open your notebooks and write today's date in the upper left corner of the page. And on the first line, write down the goal for today, which is to understand what is earth science and what is the difference between a theory and a law. So the terms we were going to define were earth science, geology, historical geology, oceanography, paradigm, astronomy, physical geology, meteorology, theory, and law. But law is not going to be in the book, so we're going to leave that one blank. I'll give the definition at the end. These can all be found. The fastest way to do this is in the glossary, but they were on pages 1 to 9 in chapter 1. The glossary just sometimes gives a more concise definition, and I'll have these all in the slideshow. So here we go. Okay, what is earth science? Earth science is the name for all the sciences that collectively seek to understand the earth and its neighbors in space. They include geology, literally means study of earth. Physical geology examines the materials composing the earth and seeks to understand the many processes that operate beneath and upon its surface. Geology literally means study of earth. Historical geology is to understand the origin of the earth and the development of the planet through its 4.5 billion year history. I put an asterisk there because this is a revised age from the 4.3 billion that they said during the 60s, which had trickled its way up through textbooks when I was a kid. So I kind of always taught it as 4.3, but I think it's been revised now to 4.5 billion years. And doing these lessons is really hard if you own a cat because they just get in your face and make it life harder but cuter. Okay. Oceanography. That's the study of the oceans and oceanic phenomena. And we also have meteorology, which is the study of the atmosphere and the processes that produce weather and climate. We have astronomy, which is the study of the universe. The Earth is related to all other objects in the solar system, so understanding them helps us understand our own planet. Okay, here we go. So theory is a phrase that gets used very loosely in our colloquial language. We'll say, I got a theory about something. We'll say that all the time. And you really don't. You have an inference or an observation, maybe a hypothesis. You don't just come right out with a theory, because a theory is a well-tested and widely accepted view that the scientific community agrees best explains certain observable facts. So theories are very strong. When somebody says, oh, that's just a theory, theories are very, 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 very strong. And theories are also, I've heard this before, theories are not ideas waiting to become a law. Theories don't become laws. Theories have laws in them, but they are two different things. They're separate from each other. Think of theories as why something happens. A paradigm is a theory that's held with a very high degree of confidence and is comprehensive in its scope. So the theory of plate tectonics is an example of a paradigm. It provides a framework for our understanding of volcanoes, mountain formation, earthquakes, continent evolution, ocean basin evolution, things like that. A law, so this is when you have to write down because this was not in the book. A scientific law is a statement or mathematical equation that describes or predicts a natural phenomenon based on repeated observations or experiments. Think of laws as the what will happen. Theories are why it happens. Laws are what will happen. All right, so scales of space and time in earth science. When we study the earth, we have to deal with a broad array of space and time scales. Some are easy and small, like the length of a rainstorm. Some are vast and difficult to imagine, like the number of stars in our galaxy. For example, the Eagles won their first Super Bowl 7 years ago. It's 2025. That was in 2018 when that game happened. The Himalayan mountains began forming 45 million years ago. So that's a huge discrepancy in time. You know, one is enormous, one is just a few years. So, for the past 200 years, scientists have developed the geologic timescale. Now, with that much time and that many smart people, the timescale must be pretty easy to understand, well thought out, and streamlined, right? There it is. And this actually, I think, has been revised even further. We have this. I'm going to bring the mouse pointer in. Hopefully, this shows up in the camera. We have this Precambrian time, which we have broken up into two different groups. And then we have this Phanerozoic time. And then within that, that expands into this, where we have, so those are the eons. And then we have these eras, Cenozoic, Mesozoic, Paleozoic. And then underneath those, we have periods in there, Cambrian period, Ordovician period, all those things. And then we have, in the Cenozoic, we have epochs right here where the dinosaurs got wiped out. And it kind of makes sense when you think about it, because, what do we have to study from Precambrian time? Very precious little in the forms of just some rocks and maybe zircons and things like that. But as you get closer and closer to today, you're going to have more evidence and fossils and things like that. So it kind of makes sense that you'd have more of these divisions as you get closer to the current period. But it is still kind of a confusing mess. So how do we get here? We can blame the British for this, as they were the most active in the early years. British names appear frequently in the scale. Devonian comes from Devon. Cambrian from the Roman name for Wales. Ordovician and Silurian refer to ancient Welsh tribes. Originally, geologic time was divided into four parts. You had the primary, secondary, tertiary, and quaternary, right? But that was far too neat to last. Soon, geologists started adding and removing divisions. Quaternary and tertiary are the only ones that survived till at least the 80s. Tertiary did not represent a third of anything because it was half of the Cenozoic, or half of the names anyway. And the Cenozoic covers 65.5 million years, and the tertiary period was 63.7 million years. So it's so confusing, these names. All right, so here's how it goes. Basically, I think today what we have is we have 4 eons. Think of these like the 4 seasons, I guess. 4 eons, 3 of which make up what we call the Precambrian supereon, because Cambrian is in the Phanerozoic. So you have that. And then the 4th eon covers the last 542 million years and is divided into 3 eras. Okay, so you have four eons. The first 3 eons are that Precambrian time. Then we have this eon, and that has 3 eras within it: Paleozoic, Mesozoic, and Cenozoic. And I think those terms actually mean like old life, middle life, new life, or something like that. And you can see, the Paleozoic and the Mesozoic are pretty big. The Cenozoic's getting a little smaller, 66 million years ago to the present. And that's when you have the age of mammals and the rise of humans and modern ecosystems and climate patterns and things like that. Okay, now, the 3 eras are divided into either 12 or 13 periods if you live in North America, which I do. They are the Old Life era, Paleozoic, which has the Cambrian period, which is why the times before that and those other 3 eons are called the Precambrian. You have the Cambrian period, the Ordovician period, the Silurian period, the Devonian period, the Carboniferous period. Okay, so Carboniferous is going to cover 2 periods in North America. In North America, we break that up into 2 different groups, the Mississippian and the Pennsylvanian, because there's a rock discontinuity in there that doesn't exist in Europe, but it exists here. So we break it up into 2. They keep it as 1. That's why everything is so confusing. Let's go with it. So just remember, Carboniferous covers Mississippian and Pennsylvanian in North America. And we also have the Permian period. All right, the Middle Life era, this is where we get our dinosaur times and all that. You have Triassic period, Jurassic period, and Cretaceous period. And that goes up to 65.5 million years ago. And that's when the KT event happened and the meteorite hit the Earth and wiped the dinosaurs out. Then you have, after that, the New Life era, where we have the Paleogene period, the Neogene period, and the Quaternary period, which is 2.6 million years ago to today. Now, you would think that would be enough, right? No. Charles Lyell added epochs to cover the period of time since the age of dinosaurs to today. And again, I can't blame him too much because there's a lot more fossil evidence to go through and look at. So, all right, here we go. So we've got epochs from 65.5 million years ago to today. And those are the Pleistocene, which is the most recent, the Pliocene, which is the more recent, the Miocene, which is the moderately recent, and the vague Oligocene, which is but a little recent. All right. So hopefully this makes a little more sense when you look at it. This tertiary period, I believe, is now gone. And I think it's just these three, the Paleogene, Neogene, and Quaternary periods. And then all the epochs from the time the dinosaurs were wiped out to today. So it is fair to say we are in the Holocene epoch of the Quaternary period of the Cenozoic era in the Phanerozoic eon. It's as simple as that. See, it's real easy. Now, in class, we were creating a timeline of geologic and historical events using calculator paper. So it's like receipt paper. And I had the kids work in pairs and doing the math with brains. We made it real easy. The scale was going to be a meter is a billion years. So it's all like working in the metric system. So you're just moving decimals around and figuring these things out and figure out how the timeline is going to work, given that if you take 4.5 meters of adding machine paper, I think it's called adding machine paper, and roll it out and cut it, all of modern humans fit on a line at the end of the ribbon that's thinner than the graphite in your pencil. So the challenge there is to figure out how you would make that work and how you would represent that on your timeline. Or, here's a hint, timelines. Okay? Anyway, I hope you enjoyed that. I hope you have a better understanding of our geologic time and how that geologic timeline chart works, because when you look at it, it is overwhelming in how confusing it is. Anyway, hope you enjoyed this. Have a good rest of your day.